Okay, so let's consider the next scenario, which is Poiseuille flow. So Poiseuille flow, unlike the Couette flow, this is nothing but the pressure-driven flow. So let me explain the scenario here. Okay, you have let's consider the space between the two plates. We have a space between the two plates, and then there is a top plate, and then also bottom plate. Both of them are stationary. Hey, so in this case, we are applying some kind of pressure here, and then that is going to deliver the fluid. Okay, it's going to create some motion of the fluid particle here. Okay, so in this case, okay, just for the sake of the argument, let's consider the two location in the upstream and the downstream. Okay, if we say, if we put the pressure from the left to right, flow is occurring from left to right. It's also fair to say. And then, so at this point, this is the P equals to P1. At the downstream, it's a P equals to P2. Okay, and then for the sake of the argument, let's also set the coordinate. So we are going to put the x-axis in the midline between the plate. This is the and then this y is the the distance between the plate, just like a Couette flow. And then this z is going to be out of the plane. Hey, so in this case, okay, top of the wall is the this is the positive h. And then bottom of the plate is the negative H. Okay, so with this, okay, we are going to consider the pressure is going to push this fluid in the certain direction. Okay, so the of course it might move into the direction of the U. It may move in the direction of the V, or it may move in the direction of the U, V, and then W. Okay, so at this point, we didn't make any assumption, we didn't make any judgment. But is this is this going to be causing any kind of flow? We would like to postulate. Okay. So for the for the completion, okay, this fluid has the viscosity of the mu and then density of the rho. Okay, and then in this case, okay, for the sake of the argument, let's just also call this is the x at this point is the x1, and then x at the downstream is the x2. Okay, so in this case, we have a pressure at the at one is the upstream. Okay, this is the pressure at the number one. This is pressure at number two. Pressure at one is always greater than pressure at the downstream, right? I mean that sort of makes sense because otherwise flow is not going to occur. So when we define the pressure drop, usually this is defined as the P1 minus P2. Okay, so this is the we can say the this when this happens, pressure decreases. Okay, a pressure decreases over the distance between the okay, x1 minus x2, okay, or x1 and x2. And then we can also say here, in this case, let's just say, the distance between these two locations is the L. Okay, so in this case, that's the yeah that's how we define it. Okay, then We can actually, this is more like an interpretation here. Since the geometry is uniform, is the uniform along x, it means, it doesn't become, the suddenly wider or narrower, right? They always, the having the distance, keep the same distance between the two walls, okay? Since the geometry is uniform along the x, okay, pressure decreases linearly, okay? This is the pressure decreases linearly along the x. Okay, so what does that mean? Okay, if you want to describe this, okay, this how this p decrease over the x, right? Then it's going to be usually, right? This is the how we want to describe here is the p2 minus p1 equals to this is no x2 minus x1. Okay, so this is the x2 minus x1 is the just the distance. Okay, this one is the x2 minus x1 equals to this particular distance L. And then P2 minus P1 is going to be, this is the opposite, it's actually the negative of the delta P. So it's going to be delta P over the L. Okay, so in fact, the pressure is going to decrease. I mean, the pressure is going to, usually pressure is going to cause a flow from the region of the higher pressure to the lower pressure, right? So this actually doesn't make sense. In fact, this is going to be the P is the decreases, and then of course this is the negative sign, right? This is the negative slope, right? So if we want to draw this, I mean again, just for the sake of the completion, we can consider this is the two location. We have a two location at the x1 and the x2, and then at the p1, this is the higher, and then this is the p2, right? So this is the like this is a location at 1, this is a location at 2. And then if you want to have some line, right? Some lines, they are going to go down. This is the really what I mean by the, maybe I can put it with the regular line here. This particular negative slope is the really meaning this, okay? So anyway, this is just a little bit of the setup. Okay, what we want to discuss now, anyway, is we would like to discuss the Poiseuille flow. Okay, now we want to know how this, by solving Navier-Stokes equation, are we able to, identify how the flow looks like between these two walls when fluids are pushed by the pressure. Okay. So let's do the same thing, the step by step. First step we do is the postulate a solution. Okay, so we start with the this it's always the velocity, right? This velocity is the ui plus vj plus wk. Okay, so then in this case, okay, this is the let's do the very similar consideration. Okay, so and then we have this fluid particle. Okay, this fluid particle can move potentially in the direction of the u, or in the direction of the v, in the direction of the w. Okay, so pressure is coming along the x direction. Okay, pressure is only applying to the x direction. Okay, so this is really the it's very similar to the how we analyzed everything in the quick flow. Okay, so first of all, right, is there any vertical flow? I mean, is this by this pressure, does it push the fluid up or down? Probably unlikely. Okay, so no flow in the y direction. Okay, let me just write this. Okay, this is the x, y, and then z, right? No flow in y, and then this is telling you the v equals to 0. No flow in the z direction. They don't come out or they don't go into the page. So this is going to be probably we can say w also equal to 0. So flow is in the x direction. In the x direction. So u is going to be a non-zero value. Okay, this is probably agreeable here, right? Okay, so this is nice. So let's just say in this case, this is very similar. Okay, we have a three terms. This is likely. This is likely equals to 0. This is likely equals to 0. This is the only remaining term here. Okay. Then the what we can say here is the now u can be potentially it depends on the four variables. Okay, you can depends on x, y, z, and t. Okay, so argument is really the same. Okay, let's just assume steady state, which allows you this is the no t dependence. Okay, the alternatively, if you look at the the different z location, okay, so if you consider this particular fluid particle, okay, the if you consider, okay, maybe let me just put it here once again. So the assume steady state, no t dependence, and then if you take a look at okay, this fluid particles at the different x location, okay, in this case, once you achieve the steady state, this, I don't think they are going to change the fluid velocity anymore, right? So this is going to tell the no x dependence once they become steady. Another consideration is the if you take a look at these particles here, okay, if you look at this z direction, if you compare these three fluid particles, right? As long as they are the same level here, they should be moving at the same speed. Okay, so this is the U has no z dependence. Okay. Okay, so that's really the things. Okay, so perhaps though, if you compare the fluid at the different location, okay, between the wall here. Okay, so here's the at this point we don't know, but it's probably reasonable. If you are far away from the wall, you are feeling less shear, right? It's probably easier to move. Okay, so something like this. Okay, we don't know exactly the form, but the most likely, um, if the fluid particle is away from wall, move faster. Maybe. This really consideration is the it's if you say it here, okay, this is DE. If you to avoid any ambiguity, this direction is the y direction, right? So therefore, this is DE, no DE. There is DE, y dependence. Okay, so in fact, to summarize, the originally this the velocity or speed u can potentially depends on 4 different variables x, y, z, and t. However, in this case, okay, for the completion, you can say this is x. Okay, for the completion of the argument, it does not depends on t because it's steady. It does not depend on x as long as they establish the steady flow, and then it probably also doesn't depend on z. So most likely, what we can take here is du equals to u of the y. Okay, so indeed, this is the postulated solution. Okay, so this is, in fact, you may have noticed the argument is quite similar to the create flow, but it's really nice to practice at this point. Okay, so we just yeah did the same argument here. So in addition to this, okay, we have two other u equals to u of the y, and then there is no flow in the v y direction, and then there is no flow in the z direction. So this is the another two solution, postulated solution. Okay, so let's just check. Okay, let's just check if this, the postulated solution satisfy the continuity equation. If the postulated solution satisfies the continuity equation. Okay, so this is the for continuity equation is the nabla dv equals to 0 for the because we assume the steady state, okay, steady flow. So this is the same thing. Okay, I'm just the skipping here. Okay, this is the left hand side equals to this the nabla dots dv's. Okay, so this is the ddx of the low u plus ddy of the low v plus ddz of the low w. Okay, and then our postulated solution, this is the solution equals to u equals to u of the y, v equals to 0, w equals to 0. Okay, so I just the check here. Okay, so argument here is the v equals to 0. So most likely the middle one equal to 0. Okay, so anyway, let me just write this explicitly. Low u of the ey plus dy of the 0, ddz of the e0 equals to, again, the first term is to just disappear. So, so this is great. This is going to, we say this satisfies continuity equation. So at least, our postulated solution is a good candidate. It's a good candidate for the, the potential solution for the Navier-Stokes equation.